All right, let's continue with our new lecture. So last time we talked about the one sample use statistic, but if your statistic wants to compare multiple samples, then this is the more general case. So essentially, we are under the case of having S samples. So now we need two sets of indices. So index I for indicating the sample index. We also need an index for the within sample index. So in this case, the statistical functional can be defined in a more complicated general way. That is, we need M1 random variables from sample 1, from a distribution of sample 1, M2 from distribution of sample 2, and MS from a distribution of sample S. So therefore, correspondingly, when you construct the U statistic with sample without replacement, this is what you get, right? From N1 choose M1, N2 choose M2 to NS choose MS. And you need to have these S sets of samples. So yeah, essentially, this is the most general case. And also, if you do the, how to say, if you want to, let's look at one example. Let's say S is 2, means 2 samples, M1, M2 are both 2. You need 2 arguments for each sample. And if you define this G to be this function, that is, you compare y12 minus y11 to y22 minus y21. So just to clarify, these two are from sample 1. These two are from sample 2. Okay, so essentially what you're doing here is that you are evaluating the relative consistency of rank within each sample. In other words, can I say that? Y12 minus Y11, Y22 minus, no, I shouldn't say it. It's not relatively rank consistency. It's basically you're comparing the difference between the two things in each sample, right? Two IIDs from each sample. And you want to know whether the difference is bigger in sample 2 than in sample 1. And then essentially, when you calculate the use n statistic, you are basically getting samples from your sample 1, INJ from sample 1, KNL from sample 2, and you compare them, and you do all sorts of comparison, all cross comparisons. And this is statistic that has been proposed for testing that F1 and F2, they are the distributions of the two samples, differ only by a shift against the alternative that F2 is more spread out than F1. That's what I'm saying. Yeah, because you random pick two things, the spread is bigger in sample 2 than sample 1. Okay, so in other words, you can see that there are many statistics you can construct as U statistic, right? As long as you do sample without replacement. And okay, and let's look at the result. So for multi-sample U statistic, we can also do the H projection. But here the projection will also be as things, right? You project sample 1 to M1 to K1, M2 to M2 to K2, MS to KS. You do these projections. So as a result, you can have these complicated sigmas. Previously, we just have sigma 1, sigma 2 to sigma k squared. Here we have sigma k1 to ks squared. So everything becomes s-dimensional. Okay, anyway, so coming back to the theorem. This is the important thing for such an S sample U statistic result. Suppose that for sample I from 1 to S, xi1 to xiny is a random sample from the distribution fi, okay, ith sample, and that these S samples are independent of each other. They are independently sampled. Suppose further that there exist constants rho 1 to rho s in the interval 0 to 1, such that ni over n. This is the sum. This is the total sum. Okay, so basically big N is equal to N1 plus 2 plus ns, the total sum, and I over the total converges to a proportion rho I for all I, and that this sigma m1 to ms squared is finite. So this is just the covariance of everything. Okay, it's just the covariance of g y1 to ym1 to ys to ys1. Yeah, so everything, that covariance function. So therefore, this is the asymptotic normal distribution for such a U statistic. But remember, it's a little different from what we had for single sample. For single sample, what we just showed you is m squared sigma 1 squared. That's the asymptotic variance. But here the variance has s things add up together. Okay, so it's m1 squared over rho 1, over its proportion. And this sigma 1, 0, 0, 0 squared means that we're looking at the projection only to the first sample's first argument. And this one means we only project to the last sample's first argument. So adding these up. So still, we only consider the dominant terms in the variance term. That is, we consider one overlap within each sample, and we don't consider other samples. And also, you can see that if a sample has a small sample size, right? Small sample size means rho 1 is small proportion, it will inflate the contribution of its variance contribution. Yeah. So that's it. Oh, another thing I want to say here is this M thing. M is number of arguments in defining the functional, statistical functional, and also the U statistic. It also affects the asymptotic variance. So in other words, M bigger means that your parameters are also more complicated, right? While if M is 1, it means that like sample mean, it's just a functional, right, up with just one argument. So the complexity enters here, and also sample size enters inversely. So these are all the intuitions we get from here. Okay. But I would say, even though we're using the general notation, but in most cases, you only consider at most 2 samples, right? Like 2 sample comparison. Okay, let's look at some concrete example. Or maybe before we do that, let's just look at, finish the sentence here. Simpler case S equals 2, M1, M2 equals 1. Okay, so here's a 2 sample scenario, but our statistic is only involving 1 argument in G. So first order parameter and statistic. So UN, 2 samples with sizes N1 and N2. I goes from 1 to N1, J goes from 1 to N2. G apply to X1I, X2J. So in this case, I1 and 2 indicates sample. I and J indicates the index within the sample. Okay. Equivalently, we may assume that X1 to Xm are a simpler random sample from F, and Y1 to Yn are simple random sample from G. So that will give us this U statistic. So using that theorem, here is the asymptotic variance, sigma 1, 0 square over rho, sigma 0, 1 square over 1 minus rho. So essentially, sigma 1, 0 square means that you overlap in the first sample, but you don't overlap in the second sample. And 0, 1 means you overlap in the second sample, but you don't overlap in the first sample. Okay. That's the simplified version for that result. Let's look at this example, which is Wilcoxon rank sum test. For independent random samples x1 to xm from F and y1 to ym from G, consider the Wilcoxon rank sum statistic W defined to be the sum of the ranks of yi among the combined sample. So in other words, we pulled x1 to xm, y1 to yn, these m plus n things together. We call that combined sample. And then we record the ranks of y1 to yn in the combined sample and take the sum. That's why it's called rank sum test, right? And previously we have the sign rank test. You saw why? Because we have the sign indicator, right? Indicating function for the sign multiplied by the rank. Okay, so the W statistic is defined as n times n plus 1 over n plus double sum. I goes from 1 to n, j goes from 1 to m. Indicator function xi less than yj. Okay, what does this mean? So this is actually meaning that, how do we interpret this W formula? Okay, because if none of y1 to yn is greater than x1 to xm, it means that y1 to yn are the smaller ones, right? Then the sum should just be n times n plus 1 over n. That's it. And if one xi is smaller than yi, then the rank of yi is increased by 1. So basically, this you can consider the first term to be the baseline ranking if y1 to yn are the smallest. And if you have the each xi, as long as it's less than yi, you push the rank of that yj. As long as xi is less than yj, you push the rank of yj. So yeah, this is just a way to decompose it. So you are basically getting the increase. Yeah. I think there's a mistake. I think it should be 2, right? Instead of dividing n here. Yeah, that's the typo here. Okay. Yeah, I think this is consistent typo. Therefore, if we let gxy be indicator, because this is the where we need a g function, the general notation in the U statistic, then the corresponding two sample U statistic is related to W by this, right? You have the m times n here just to get you out of the U statistic. U statistic need to divide this by m times n. Okay, therefore, the asymptotic result for U statistic can be applied here. So this is our G function. Remember that comparison of the order indicator function for that. Note that theta as expectation of the G. That's how we define parameter, is probability as x less than y. Then theta 1, 0 square is the covariance of these two things. And as each one is an indicator function, we can show that it's again, using the fact that covariance is expectation product minus product expectation. And the expectation of product of indicator function is just a probability, right? So it's just a joint probability that x1 less than y1, x2 less than y2, minus square of one probability. X1, yeah. And analogously, this is the sigma 0, 1 square. So for any distributions f of x and g of y's, these variances can be evaluated numerically and in a few cases analytically. So under the null hypothesis, that's where the Wilcoxon rank sum test has, right? The null, f equals g. Then by symmetry, if f is continuous, x1 minus, the probability that x1 is less than y1 is just 1/2. Then this becomes just 1/2, this becomes just 1/2. And this probability, y1 is less than y1, xi less y1 less than y1, x1 less than y2. Because these three things are IID from the same distribution f equals g, 1/3, right? Yeah, so therefore you can easily calculate as 1/12 for both these two things. And then you can just get this asymptotic distribution. Yeah, based on the theorem. That's it. Nothing much. So I will say that this is the asymptotic distribution we use in the Wilcoxon rank test. And you can see that if you don't know those asymptotics, think about, let's step back. If you don't know this asymptotic result at all, how do you derive the distribution of this under null? Not easy, right? Because it's based on the ranks. How do you know you may do some permutation. Yeah, you have to do that numerically, but that's not something doable before computers. So that's why this asymptotics offer a very elegant solution for solving this problem. Yeah, using the U statistic theory. Okay. That's all I want to say. So yeah, I think for the last part, I'm going to skip it because it's going to be multivariate U statistic. So not multi-sample, but multivariate. So basically saying that you're having two U statistics based on the same sample. So you have one sample, you get two statistics, two U statistics, and you are interested in their joint distribution. Okay, but I'll leave this for you. Yeah, so this is something you can do a further reading because it's something natural given what we learned so far. Okay, any questions to wrap up? Yeah, we talk about statistical functionals, B statistics, U statistics, and essentially think about U statistics as a generalization of the unbiased sample variance. I think that's the simplest way to think about it, and it has M equals 2. So M is the complexity of your parameter and statistics, right? And N is the sample size. And the most important thing is that the asymptotic variance is only dominated by projection, H projection, Hofstad's projection to the first argument, G1. Yeah, that's how you just need to get asymptotic variance because other terms are negligible. Okay, if we have no questions, continue. I think this is a part which I'm very interested in talking about. And now you will probably see why the foundation we just laid, the statistical functional, is not just something abstract, but also useful. Okay, this is the part we do a lot in practice, the bootstrap. So bootstrap is something as a procedure, very straightforward. And I think for this class, we hope to provide more understanding on why it works. So essentially, the foundation of Bootstrap is what we said already about the plugin estimation for statistical functional. That is using the empirical CDF F and hat to plug in as an estimator for F. So as long as your parameter is a functional of F, you can do this plugin, right? And the V statistic is based on that. And U statistic modifies that. Bootstrap follows a very similar idea as the V statistic, but it's not for, interestingly, it's not for finding an estimator. So V statistic, U statistic are both estimators, right? Here, Bootstrap is not about finding an estimator, but it's about quantifying the uncertainty or getting the distribution or getting the bias and mean and variance about an estimator. Let's put it that way. So this is Bootstrap's purpose. You already have an estimator, you want to evaluate it. Okay, in many situations, we would like to evaluate the performance of an estimator theta hat n of some parameter theta. So again, theta is TF, is the statistical functional, and estimator is theta n hat. The following are some examples of estimators based on a sample from F. First, the sample mean theta n hat equals x bar is an estimator of the population mean, which is expectation of x, right, under F. Second, the sample median theta n hat as an estimator of the population median. Population median is just the 50th percentile, right? Third, the U statistic we just covered is an estimator of the expectation functional, right? That's what we just said. Written as expectation of the G function with M arguments, y1 to im added from F. Fourth, the maximum distance theta n hat, okay, is between your empirical CDF and the actual CDF. You take the supreme of the difference between the two CDF functions of the sample CDF from a given CDF F0 is an estimator of this TF, which you are interested in the difference between F and another distribution F0. Okay. So that's these are all the estimators. And the following examples are measures. We write lambda n at F of the performance of estimators theta n hat. So what do we mean by that? Essentially, we are trying to evaluate an estimator theta n hat under distribution F. Okay, that's the purpose. So first of all, the error distribution is 1 lambda n F. So you're getting what? This is the statistic we put on the left-hand side of central limit theorem. Theta n hat minus its parameter, TF. We take the difference, we inflate it by multiplying root m. We are interested in the CDF function of it, right? And this CDF function is essentially what we hope to approximate well using asymptotic distribution. That's it. So now let's look at the tail probability, or let's look at a CDF function at value A. What is the probability that the statistic is under A? Lambda and F defined in this way. Or we could normalize this root n times difference by some factor here. But anyway, so we're just evaluating some statistic under A, and we are trying to get this probability. So essentially, this is the CDF function we hope to get, right? How do we get that? And asymptotics offers one way. That's something we have been talking about throughout. Using asymptotics, we can get that. Now we will say that bootstrap can also give you that. Okay, first thing. Second thing we can evaluate or measure the performance of an estimator is the bias. The bias, you can see, is defined as expectation under F of theta hat n, right? Minus what? TF. TF is theta, is the true parameter value. So this is the bias. So both depends on F. That's why the measure is a function of F. And remember, we actually noticed that in the measure, we have this subscript n because theta hat n carries n. It's the sample size. Finally, variance of the estimator, which is also a function of, because the variance defines as variance of f theta hat n. Okay. In many cases, we consider estimating TF using theta n hat, which is often cases specified by plugin. Okay, so this is the V statistic, remember that. Correspondingly, we can consider estimating this performance. Why don't we just estimate this performance by plugging F1 hat? Same idea, but now we're not plugging the parameter for getting an estimator, but we're plugging the performance by getting a performance estimator. You see the same argument. And this estimator together with some elaborations often require is known as bootstrap. That's bootstrap. So bootstrap in a high level sense is doing what we're trying to do plug-in. We're trying to use the sample as an estimator for some performance measure of an estimator. So it's going to another layer, right? Previously, we're talking about how to construct an estimator. Now we're talking about given an estimator, how to evaluate it. And the evaluate measure itself requires knowing the true distribution, like the bias, variance, but we don't. What do? We plug in the true distribution by the empirical CDF. Okay. So this estimator together with some okay, it was proposed in this connection by Efron in 1979 and has been found to be applicable in a great variety of situations. Both theory applications are treated in an enormous literature. So I would say if you're interested in reading more about Bootstrap, so there are books, especially I think this book and this book have very detailed exploration of Bootstrap as a topic. Okay, so let's look at one very simple example about, I shouldn't say simple, but I should say look at one example demonstrating how to use Bootstrap to estimate this error probability, which is this case one here. How do we get that? Asymptotic distribution is one way, but now let's do it in Bootstrap. So example one, suppose we are concerned with the measure lambda NF defined as this error probability. By error, we mean estimator minus true parameter value inflated by root n. That's our error. We are concerned about CDF. The plug-in estimator lambda and f and hat is obtained by replacing the distribution f by the distribution f and hat. Then tf becomes tf and hat. In addition, the subscript f, which governs the distribution of theta at n, must also be changed to f and hat. So everything you write in f should become f and hat. To see what this last step means, write theta hat n as f of x1 to xn, right? Because every estimator is a function of your sample. That is, express theta and hat not as a function of f and hat, but directly as a function of the sample, x1 to xn. If, for example, this is our parameter, tf is expectation of x under f, right? So this is just the mean of f distribution. Then this f function in this case would just be average, sample mean. So the function f should have a subscript n, which we suppress for the sake of simplicity. So we don't actually add n here, but in fact, the function should depend on the sample size. And the dependence of the distribution of theta and hat on f results from the fact that x1 to xn is a sample from f. To replace f by f and hat in the distribution governing theta n, we must therefore replace equation 18 point, actually it should be 18.2 by this. So you're going to compare this one and this one. So what's different? Here, x1 to xn is from f. While in here, we add star to each xi. We have x1 star to xn star, and they are from f and hat, right? Same f function to map a sample to an estimator, but the sample is now different. Previously, we look at a sample from f. Now we're replacing f by f and hat. Then we need a sample, hypothetical sample from f and hat. So this is what we get. And correspondingly, this is the theta n hat star, right? It's an estimator based on the hypothetical sample from f and hat. So therefore, the notation can be written as lambda n f and hat can be expressed as this. So you want to scroll up. Here is the lambda and f we want to estimate, and you see inside here where is f involved? Here, probability depends on f. TF depends on f. And theta n hat depends on a sample from f. So all these things depends on f. And all these things will be replaced by f and hat. So then the probability will be under the empirical CDF. Theta n hat will be constructed by a hypothetical sample from f and hat. And this is f and hat. So that's what we get here. Okay? Yeah, so that's actually foundation of Bootstrap. Plug in. Replace everything related to f in the performance measure by f and hat. Yeah. Okay, so that's why now you can see statistical functional serves the purpose, right? Otherwise, you may think of bootstrap as a procedure, like sample with replacement, right? But why that makes sense? Have you ever thought about that? Why this is a valid procedure? Why people do that? Right, so now this is to explain that we are basically doing plugin. Okay, to understand this estimator, know that the hypothetical sample x1 star to xn star from fn hat is only a conceptual sample from this distribution fn hat. Okay, the distribution fn hat assigns probability, like I said, 1 over n to each of the observed values x1 to xn, the sample's observed values. And x1 star to xn star is a hypothetical sample from this distribution. In particular, the variables x1 star to xn star are conditionally independent. Condition on what? On your actual sample, because you're treating these values as fixed. Let us now illustrate the calculation of the estimated error probability on one example. Okay, now let's look at concrete example. I think it will become more clear. Okay. Let mean, population mean of F as our parameter. Theta is TF is expression of X under F. So that when you do plugin, you know, it's just sample mean, right? Average. X bar. It should be XM bar. And let us calculate the estimator in the unrealistic case of n equals 2. Your sample has just two values, x1, x2. So let's say that we know the two values. Smaller value as C, bigger value as D. Okay, so then the statistic value, sample mean value is just C plus D over 2. And you consider x1 star, x2 star, IID from, they are hypothetical sample from this actual sample. Then each of them would take each value with equal probabilities, half probability, right? 1/2. Then how many possible values can this hypothetical sample take? 4 pairs, right? CC, CD, DC, DD. Each with probability 1/4, right? So then if we calculate the hypothetical sample's corresponding statistic, it should be their average, right? So theta n hat here, this is the value for theta n hat. This is that. And this is the value for the hypothetical sample for the statistic, for the estimator. So it's x1 star plus x2 star over 2. Then given all possible values of x1 star, x2 star, this value, theta n hat star, can take 3 values, right? Because this average is C, these two's average is C plus D over 2, this is D. And this C plus D over 2 takes 2-fold of the probabilities, right? Because each is 1/4 and they have the same average. So this average is 1 over 2, the other is 1 over 4. So therefore, when you take the difference between statistic and actual value, or I should say, if you take the difference between the estimator value and the population version value. So using fn hat as the population, this is what we get. So theta n star changes while tfn hat fixed, right? It's just fixed at C plus D over 2, and this is their difference. And for this difference, now you see how many possible values can it take? 3 possible values, depending on this theta n hat star value. If it takes value C, then your difference is C minus D over 2. If it takes C plus D over 2, the difference is 0. If it takes value D, the difference is D minus C over 2. and the probabilities are still 1/4, 1/2, 1, 2, 1/2, 1/4. Then from this distribution, that's it. You get this error distribution. Yeah, essentially you are using that. But and what's actually underlying this is plugging, right? You're plugging f and hat to SF. But if you think about this from a high level perspective, the plugin seems to be very reasonable because you're not making any assumptions about f. You're just using empirical CDF as the only information, right? So this whole idea is non-parametric. Yeah. But on the other hand, I'm saying if n is too small, then Fn is not a good estimator for f at all, right? Then you need some assumption about the distribution of f. For example, if you assume f to be Gaussian, then you only need to estimate two parameters, mean and variance. That's it. But if you don't make that assumption, then f and hat has to be informative, right? So you see this trade-off here. Yeah, it's not necessarily which one is better. Okay, example 3. Estimating the bias of the median. Median estimator. Median as an estimator for the mean. Okay. So let theta again be TF, be the, sorry, I should say both the population and sample version of the median. Let theta equals TF be the median of the distribution F, and lambda and F be the bias of the sample median. So we define bias to be the measure, performance measure. Okay. So first, this is the bias definition, right? We see that. Then you plug in F and hat for the performance. Then you see as both terms involve F. So the first term that's involved in F is expectation. It now becomes F and hat. Theta and hat also involves F because it's based on a sample from F. We change it to theta and hat star. Finally, this is the population parameter, the median of F. Now we need the median of F and hat. That's theta and hat, right? So we change everything. So where theta and hat is the median of the sample, x1 to xn, and theta n star is the median of a hypothetical sample x1 star to xn star from F and hat. Let us this time consider the case of n equals 3. Still sample size very small, so we can do enumeration. That's why we want to do enumeration to demonstrate the idea. Again, we consider the 3 values in our sample to be sorted. Smaller one, smallest, C, middle one, D, largest one, E, C, D, E. We let them denote the ordered observations. So in this case, the median of F and hat is D, right? It's clear, it's D. And the hypothetical sample has how many choices? 3 to the 3, 3 cube, right? 3 cubic is 27 possible values, triples of values. So it can be CCC, CCD, CCE, right? We can enumerate all the possibilities. And these 27 possibilities share the same equal probability. Okay, let theta n hat star be the median of a hypothetical sample. Okay, so since it's, and we consider the median, and here this median can be C for how many cases? You can enumerate, right? So if it's the C, then you must have at least 2 C in your triple, right? So the total number possibility is 7 out of 27. With such a probability, your hypothetical sample median takes C. Similarly, it takes E is the maximum, it's the same probability, 7 over 27. And when it takes D, the middle one, is the remaining probability, 13 over 27. So essentially, you can calculate your plug-in estimator for the bias using this hypothetical sample. So you are calculating the C, D, E weighted average given their respective probabilities. This is your expectation. While D from the original sample is your theta and hat. You take the difference. this is what we get. Okay, this is what we get. And this bias, we can restore CDE as the minimum, second minimum, maximum. We put that as the origin, using the original sample order statistic notations back. That's it. So essentially, you see that to estimate the bias, we do plug in. And now this bias estimator is expressed as a function of our sample because f and hat depends on our sample, right? So therefore, it is still a function of our sample. So do you see something interesting here? That is, the estimator sample median is based on our sample, but we have only one sample. And when we evaluate this estimator's performance, we're using the same sample, right? So the bias is also estimated from the same sample. Yeah. And you can think about this as an endless discussion because you can say, what is the bias of this bias estimator? You can say that, right? So that's why statistical inference, I would say, never perfect, but we're still trying to gain some understanding about the calculation we're doing, because if you don't know statistics, right, not that you don't know, have no knowledge at all, everybody know how to calculate sample average. I think maybe elementary school, yeah, calculation, you can calculate sample average, but you don't know what that means, right? Or how much does it inform you about the population mean? That's where statistics kicks in. It's about understanding your calculation. Yeah, but a lot of the things are imaginary since you only have one sample, right? You think beyond these numbers, and yeah, hopefully you can now see this, why some people will say statistics is a combination of philosophy and mathematics and maybe some art. Yeah. Since it's subjective, I think the problem here is it's subjective. And why inference is so challenging is that you don't know the ground truth, right? You don't know the true value. Yeah. Maybe for scientific investigations, you could do validation, experimental validation, or at least I would say for clinical trials, why statistics is crucial, necessary, is because the outcome, like drug efficiency, is what we want to infer about, right? And it's so important that we make it right. So, and we also need to use statistics to make sure our clinical trials well designed, so we can better have an estimator, have a better estimate about the efficiency. Otherwise, how can we trust them? And also the trials are so expensive, right? And we need to recruit people, so it's not something that's easy to do. And so you can see that this is very, very different from prediction tasks, because for that you do have label data, right? Okay. All right, a general algorithm for such calculations suitable for small n is discussed in this Fisher and Hall. However, the numbers of distinct values x1 to xn is shown to be, distinct values is shown to be this, depending on our sample size. So how many distinct values you get for the hypothetical sample? Think about, yeah, this is a combinatorics problem. Think about the possible ways of assigning n balls to n different bins, allowing for empty bins. Okay, so what does this mean? So this is about the number of possible hypothetical samples. So essentially, you are going to get a hypothetical samples just based on the original sample, right? In the original sample, you have n values, and you sample with replacement to get an n value hypothetical sample. Since you allow repeats, that's the thing. So basically here, you assign n balls to n different things, meaning that, so I'll let you think a bit. So what do you mean by n balls? What are the balls? What are the bins? And you allow for empty bins. Yeah.
Sampling with replacement.
Yeah. But what is the realization in our case? The hypothetical sample, you mean? So let's just say our actual sample is represented by n values. And we sample from these n values. We sample n times from the n values to get our hypothetical sample of size n. Yeah. Sure.
So in this analogy, like n balls and
yeah.
bins, allowing for empty bins. So
Yeah.
I guess so each bin you have n plus one options, right? Because you can be any of the n balls or it can be empty.
Oh, okay. So in this case, I can give the answer by saying empty. It means that one, let's say the n values in your original sample, x1 to xn, right? By saying empty, it means that some values are not sampled. They were not sampled, but some values can be sampled repeatedly.
Oh.
Yeah, right? Right, exactly. So essentially, I think besides this ball and bin thing, maybe it's better to think about, I think another way to think about it is that you have how to say, you have n values here, and you can actually basically set up bars to separate them. Yeah, by setting up bars, it means that, okay, I need to set up n minus 1 bars anywhere. So then with the n minus 1 bars, I'm creating n bins. And given that, I have the assignment, sample with replacement. Because it's like, okay, if my between the two adjacent bars, if it's empty, it means that that value is not sampled, right? Yeah. If it has two, it means it's sampled twice. Yeah. So therefore, it becomes, where do we set up the n minus 1 bars given the n values? And that's actually it's actually n plus n minus 1. So n values plus n minus 1 bars, and decide where the bars are. Yeah. 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 So you see what I mean, right? Yeah. So because once you have the bar set up, you can actually know the samples, right? You know how the sample works. Yeah. Maybe it's easier. I draw a analogy. So it's like this, like n equals 3. Okay. One thing is that I set up the 2 bars in this way. So what does this mean? It means that first value not sampled, second value not sampled, third value sampled 3 times. This is what I mean. And if I have this, like this, then it means that each value sampled once, right? And if I have this, it means that, okay, first value sampled 3 times, second value not sampled, third value not sampled. Yeah, so that's why all these scenarios represent one type of hypothetical sample. It's about where the bars are put. And since the bars can be ordered in any way with dots, both. So that's why it's n plus n minus 1 bars jointly chosen, right? That's how this works. Yeah. Does that make sense to you now? Okay. Yeah. Okay. I think combined hierarchy is very fun, right? Because we think about the other possibilities. Yeah. Yeah. Okay, so, but the thing is, the distinct sets of hypothetical samples can grow large. For example, for n equals 10, this is the total, 92K for n equals 10. So that's why when your sample size is large, these enumeration, like what we did here, getting the exact lambda n f n hat is impossible, right? You cannot afford to do that. N equals 2, yes. N equals 3, yes. But n equals 10, no, right? So that's why we cannot get, so the question here is, this thing is what we want, but it is very hard to compute. That's the problem. That's the problem. Then what do we do? we are very close to the actual bootstrap we use in practice. That is, we don't consider all enumerations of hypothetical samples. We just consider a subset of them. We just, for example, we don't go through all these 92,000 combinations, possibilities of hypothetical samples. We maybe only randomly pick 1,000 of them, right? And then we use that 1,000 to compute an average of this performance measure and use that to approximate this, and that is called Monte Carlo approximation. Yeah, so Monte Carlo essentially is that we don't get the full distribution. We sample from it. As long as we sample enough, then the average of that is a close approximation to the mean of the true distribution. Okay, so one thing to think about the difference between Monte Carlo approximation and estimation is that Monte Carlo is something you do, is that you do repeated sampling and do the average. While for estimation, it's based on a sample that's given to you. So you basically have no control of the sampling process anymore. You just get one sample and do some calculation, and then you imagine what's out there. Yeah. Okay, let's see. For large N, this difficulty creates a strange situation, right? The estimator lambda n fn hat is a well-defined function of the observations, but in practice, we are unable to compute it. The seminal paper Ephron provides a way out, bootstrap. Okay, so bootstrap is what? Now let's summarize what I just said. So the bootstrap basically use Monte Carlo approximates plugin. Okay, and in the plugin, you are basically using fn hat to estimate f, right? And that's the true performance measure. Yeah, so essentially, we are interested in the true performance measure of an estimator, but we cannot do that because that depends on the knowledge of f, true distribution. We use plugin to replace f by fn hat, but then since n is large, computation is too challenging for that performance measure based on fn hat. Then we do Monte Carlo approximation, and that's bootstrap. Okay, now let's look at this example, bootstrapping a probability. Since this is the performance measure plugin, fn hat, where x1 to xn star is a sample from fn hat, and since fn hat, the empirical CDF is a known distribution, evaluating lambda and fn hat is a special case of the problem of calculating the probability. So S and okay, so I would just say this is quite abstract. We can just make it a little bit simpler. I think I already said it, so you can ignore the notations here. I'm just trying to say that here, if you want to enumerate all hypothetical samples, it's not possible, but you can just get a subset of hypothetical samples as long as your sample size, as long as the number of times you sample from the actual sample is large. Okay, if you sample capital B times, that's it. And yeah, that's pretty much it. So you just sample from x1 to xm for capital B times. As long as your B is large enough, say 1,000, then you can say your approximation of the performance measure is close enough to the true lambda n fn hat. So essentially, in order to apply this idea to calculate this lambda and fn hat, we must drop capital B samples x1, xi1 star, xin star from fn hat. And this is B hypothetical samples. Now we give this name, bootstrap samples. And essentially, how many times are we sampling? B times N times, right? Because for each hypothetical sample, we need to sample N times. So each takes the original values, original observations x1 to xn with probability 1 over n. The situation is a special case of the general case described above. Okay. Yeah, okay. So anyway, okay, let's just read this last paragraph. As is in the general case, the estimator lambda and fn hat based on the plugin is approximated by the frequency lambda bn. So remember here, this depends on the number of times we sample. So that's why we have this capital B here. And this is the notation we use as the performance measure from Bootstrap. This approximates this, okay? And this estimates this. So let me just try to summarize a little bit. Lambda b n star approximates lambda n f n hat, which estimates lambda n f. So there are three things here. Okay. So we use two ideas, Monte Carlo approximation and plugin estimation. Yeah. Okay. I think for the end, let's try to look at one example and then we can wrap up this lecture. Bootstrapping and expectation. Bootstrapping is not restricted to the case like about this error distribution as in example 4. Suppose that we're interested in estimating the bias. That is, expectation of an estimator as a function of the sample from F minus the true functional of F, true parameter functional of F. Put some estimator and some parameter. Then by plug-in, F becomes Fn hat, and we have a hypothetical sample from Fn hat, and Fn hat plugins F minus the T Fn hat. And we saw in example 3 that difficulty of computing expectation of Fn hat given that exponential number of possible hypothetical samples. So therefore, we draw capital B bootstrap samples from the original sample. And from each bootstrap sample, we compute this theta n star, right? And here we denote this as I, as the ith bootstrap sample. And we compute our statistic. So you can see that we will have capital B of those. So instead of calculating this expectation, which is under Fn hat, which is difficult to compute, we approximate it by the average 1 over capital B, I from 1 to B, theta hat I n star. That's what we're doing. Yeah, we compute the statistics on each bootstrap sample and calculate average, using this average to approximate expectation under Fn hat. Because exact expectation will need enumeration, right? That's it. That's the bootstrap version for the bias. By the law of large numbers, this bootstrap version will converge to the plugin version as long as our bootstrap sample number capital B is large. So for this part, it is under our control. But what is not under our control is how well is the plugin estimator. That's a separate question. And that's a question Bootstrap cannot resolve. So just for your information, you can conclude that Bootstrap only works well when plugin works well. I think this is something maybe you won't learn like if you just learn the procedure, right? Okay, let's read these notes. I think these are the things we can summarize and stop here. Bootstrapping introduces a new element, which at first may be somewhat confusing. You know, the term bootstrap means self-saving, right? You're self-saving using the same sample to save you, right? The following comments may help to clarify its basic logic. Note 1. It's tempting to think lambda bn star, the bootstrap version, as an estimator of lambda and fn hat, the plugin estimator. However, lambda and fn hat is not an unknown parameter, but a quantity which in principle is known through, though it may be difficult to calculate. It's only computation bottleneck, but it's not unknown. The bootstrap sample avoids the necessity of performing this calculation, enumeration, by providing an approximation we termed lambda bn star, which for large B is nearly certain to be very close to lambda and fn hat. Thus, lambda bn star is an approximator rather than an estimator of lambda and fn star. Note 2. An objection that may be raised against the use of lambda bn star as an estimator of lambda and f is that it depends on the bootstrap samples and therefore introduces an extraneous randomization into the inference, right? It's random. A repetition of the process would, with the same data, x1 to xn, generate another bootstrap sample and hence a different value for lambda bn star. This argument loses much of its force by the fact that for given x1 to xn and sufficient large B, the approximation, though a random variable, is with high probability close to the constant, right? If you repeat this again and again, because as long as B is large. Note 3. On first encountering the bootstrap idea, one may feel that it achieves the impossible to provide additional information about the performance measure lambda and f without acquiring more data, right? That's called self-saving. This is, of course, an illusion. The estimator lambda bn star is not an improvement over lambda and f and hat, that's what I said, which remains the basic estimator. What lambda bn star accomplishes, and this is very useful but not a miracle, is to provide a simple and for large B highly accurate approximation of the plugin estimator, when the latter is too complicated to compute directly. Okay, the two-stage process I already said. Estimate the true performance measure by plugin, approximating the plugin by bootstrap. The method is in fact much more general, with many alternatives being available for each of the stages. Regarding one, depending on situation, quite different estimators may be used, right? You can use empirical CDF to do plugin, or you may use a parametric version estimator to do plugin, right? And the following example for just one illustration. Okay, so I think we will stop here. Hopefully, I think now you will see that Bootstrap is not a magic. As I mentioned, it's still like this thing must be a good estimator. That is the most important thing. If it's not, then nothing works. Yeah. Okay, so then I guess I'll see you next Monday. Yeah, thank you. Yeah, so